Welcome, ladies and gentlemen. Today we are going to start talking about chapter 43, which is going to cover your immune system and really just talk about how your body is able to fight off or prevent infection in the first place. A couple of things I want to kind of point out here. This is a complex system in the sense that there's a lot of things that are going on all at once, and there's also a lot of interplay between other body systems. So it can get really easy to get lost in all of the details. So make sure you're taking your time with this, make sure you are spending time with this, but at the same time, try not to get too lost in all of the details and the nooks and crannies either. If you can flush it out and figure it out, that's awesome. And that's going to hopefully set you up really well if this is something you end up studying again in the future. But that being said, I'm going to throw things at you as exposure. If things aren't making sense, please come see me. But otherwise, try not to get so bogged down in the details that you're missing the overall point of how the system works. Okay, so just kind of something to keep in mind as we're moving forward through this one. Um, First off, we're talking about a way for your body to take care of disease. So we're talking infectious diseases. So let's kind of just start there before we start digging into the system that takes care of it. Um, so we're talking about a disease that is caused by a pathogen, which is really the crux of this germ theory of disease. So a pathogen is a disease-causing organism. Those can include bacteria, they can include worms, they can include fungi, so on and so forth. Anything that causes a disease or a virus. And the reason they sort of distinguish organism from virus is because we talk about viruses and the question of are they really alive, are they not alive? Um, and they really sort of are this weird entity unto themselves. So when we look at pathogens, they really are of extraordinary diversity. Um, every organism that we know on Earth, every life form on Earth is susceptible to its own set of pathogens. And even within that single organism, the amount of different pathogens that can infect that organism is also pretty diverse as well. One of the things that a lot of pathogens have as a benefit evolutionarily to themselves is that they often also are capable of relatively rapid evolution. And so they're in this constant co-evolutionary arms race between the host trying to evade the pathogen itself and that pathogen trying to get what it needs. Um, and ultimately, that pathogen is in its host to reproduce. And the question then just becomes what is it doing to the host in the process of getting what it needs to replicate itself and move on to the next host that it can infect. So there really is this virulence trade-off in these pathogens. So we talk about virulence, we're talking about how infectious is it, how quickly does it spread from one host to the next, and what sort of damage does it end up causing to the host as a result. The more virulent, the more severe the disease is for the host, that means that that bacterial cell or that virus or whatever pathogen you're talking about is really good at making lots and lots of itself. It's really effective at taking over the host using its machinery, whatever that may be, the host's materials, to make more of itself. The problem is the more virulent that pathogen is, the more likely that you end up feeling like complete crap. You never get out of bed. It may just kill you. And the quicker that happens, the less likely the transmission, the less likely that pathogen then makes it to its next host. So the benefit there is I'm making lots and lots of myself as that pathogen, but the trade-off then is that I'm not as easily able to access my next host if my current host never interacts with anybody. The opposite end of that spectrum then is to be less virulent, where you aren't as effective at producing lots of yourself, but as a result, your host doesn't feel like complete crap, um, is able to get up, still kind of function with some more mild symptoms, and as a result, is probably interacting with a lot more of your host vectors. Um, so think of something like the flu, and a very bad case of it, mind you, where you're really just kind of laid up on the couch for days. You're not interacting with a bunch of people, and so you're not passing on that pathogen. Something more like just a general sniffle, a common cold, maybe you don't feel as crappy. That cold virus isn't reproducing as quickly in your body and making as much of itself, but you are going to school, you're going to work, you're interacting with people, and so that cold can continue to spread. So there's a definite evolutionary trade-off here to how virulent you are as a pathogen versus your ability to transmit to your next host. Um, so lots of coevolution going on here. For us, we have an immune system. Not every organism does, and even organisms that do have immune systems will work a little differently at different levels than what we see in humans. So we're going to kind of really focus on human immune system from here on out, but know that other organisms have them. They just may work a little differently, or just not as at the same complexity that ours does. So if we talk about the immune system in humans, what is its overall goal or overall function for your body? Why have we evolved this? What sort of jobs does it do for us? And most students can pick up on the first one, being able to recognize that it's your defense against infection. So get defenses against bacteria, against viruses. We can use vaccinations as a way to boost those immune defenses and protect you against infections without ever making you get sick in the first place. Um, but it's not the only goal, it's not the only role that immune system plays in the human body. Um, we'll talk mostly about that one because it's one that we understand the best, and it just happens to fit within the context of what we're talking about in this unit. But your immune system also plays a role in defending against tumors. It is designed to be monitoring your body for cancer cells and to get rid of them before they really ever show up in a scan for cancer. Um, they will also, cells in your immune system will also work to clear out dead cells, to do tissue repair, so you get some sort of cut or scrape or break, and cells of your immune system come in and help to restore that tissue. They can also work for just injured cells uh, and work on inflammation, some of which is a good thing. Others, when it's causing inflammation and it shouldn't be, can cause things like allergic reactions, autoimmune and inflammatory diseases. So definitely implications there in terms of when it goes haywire. And your immune system also prevents, or I should say complicates, some other metabolic, or excuse me, medical procedures. So tissue grafts and gene therapies and things like that are complicated by your immune system because your immune system is supposed to recognize when things don't belong to you, to get rid of them, which ties back to their ability to help you defend against infection. But when we want your body to take on that heart transplant, or we want your body to allow us to introduce this protein or this gene, or whatever the case might be, we end up fighting the immune system's natural reactions to those. So we have to employ things like immunosuppressant drugs and things like that to hopefully get your body to kind of chill out and not do its job, um, because we need it to be less aggressive, for whatever that particular medical treatment is at the time. But the flip side to that does mean that then you are more susceptible to infections, and so there's a lot of complications that come along with that.